Others shall be joining or not. I am recording it, and whatever I shall be doing, the annotations I shall be doing through this. Okay, not using the board so that people can understand what I am trying to say. So, should I be waiting or should I get started?
Yes, sir. Position is just so I want to they will be they are done. Bhushan stopped by and said that he wants to continue the project. I think actually they have a farewell party. Oh, it must be a holiday. Oh, okay.
Anyways, like let's get started. I shall
Make it full screen.
like it is full screen on my laptop. Okay, that bar is there. I don't.
Side, if you see the laptop's full screen is being shown over there.
Huh.
That's just oh. Is that 9:10? Oh, okay. It's an aspect ratio.
Aspect ratio.
Oh, let's start.
Yes. So is anything showing on Teams? Please check. Otherwise, there is no point of recording. Just showing, right? Uh, so let's get started here. So basically, yeah. Basically this PyTorch 2.0 stack is like a bit complicated in some sense, but it mainly just the ballpark. It mainly deals with three IRs. Okay, first one is torch IR, then there is attain or frames IR.
Okay, before we get into the details,
Uh-huh.
why don't you actually tell like what was the part cost? Why somebody wanted to completely overhaul and have the PyTorch 2.0? Then people can actually relate it better about what you are doing. So this is the advantage, general advantages of how to actually communicate.
Uh-huh.
Tell the purpose first before getting into how something is done.
Okay, so basically what happens here is something like this. So Python, PyTorch are like interpreter based. Like Python is interpreter based programming language, and Python and PyTorch is a library written on top of it. So basically, what happens is you are interpreting the program in some sense. Now they have they are always trying to do some kind of a compilation sub just in time compilation. Based on that, they had some approaches like JIT script, JIT trace, something like that. They had previous compiler versions, but problem there was they were doing static analysis of those things, and as a result of what, like they were having a lot of issues in there. As in, if there is an if-else condition in your program, so it might give issues. Okay, so while you are tracing it in some manner, trying to compile it, like it would be like that if condition which was there, right, would get hard coded in the program in some sense, like the compiled version which you were trying to do. These were like previous few of their compilation attempts. And apart from that, like there are few, like one is JIT trace and another is JIT script. So one of them was having this problem. Like JIT script was like you have to compile it, but if else conditions had issues. But there was another thing like JIT trace and all, where they could deal with this if else conditions properly. But for each of the data type, you had to give type annotations for it, and it was a pain because Python being a dynamically typed language, you do not, as of now, understand like how, like, and what data mappings it might have. Like you might not know, okay, like what might happen in some sense. There is like complex operator overloading and all, method overriding. So basically, to do away with this thing, they were keeping in their mind to come up with a new compiler altogether, and their main plan was to keep this entire thing close to the Python level, because like what their claim is, if things are pushed on to the CPP side, so they get less number of contributions from people, because actually, like what they complain is, if you are making a simple change to the C++ program, it was a huge stack of like recompilations and all, and it causes delay. So what they tried to do was keep things close to the Python level and push things off to the like C++ side as on only when it is super necessary. Okay. So even Utkrist was saying me that day, like he made some few changes to caching allocator and it caused a huge compilation. Like that is a problem. So their approach is Python first, okay, and yeah,
So
compilation.
this is primarily they are saying that even if it's an overhead during development time, not necessarily at runtime. Right?
Yeah, that is
It's a
like
development
yeah
time.
development time. So they are saying ki, like people if if issue like if they have to make some contributions on the C++ side, they saw ki, like people coming up with enhancements and all are quite less, and they saw ki, like the number of lines of code with people come up on the Python side of the thing, like that dots slash those kind of stuffs. They saw ki, like there are more number of pushes from people like pull requests or something like that. So they to keep the community system interactive and all, they came up with this idea. And also one thing which they were saying is like you do not need to just compile the C++ side again and again. You can just make changes into the virtual environments Python files and you can just test it as in the fly. So it makes integration much easier. So so basically they came up with something known as compile. Okay. So it is kind of a magic method. So if you are having some say like some class which is say my module and it is inheriting from like torch dot nn dot module. Okay, this is one instance ki like this is the module like the base class for creating modules in PyTorch, right? And this is one way of creating your custom module, or you can also create a like a basic function like define function. What happened? Please check, like I don't want to switch the screens and all. Hmm. So like there is a function like just using curly braces anyways, like you can have functions in here. So how do you convert something uh, like or do you intimate your intention ki like that you want to compile this stuff. So what you basically do here is something like this. So if you are having a module, so say m is module and you instantiate it as my module, okay, then what you can do is to torch compile it, you do compile, say this is a new variable, and you take this module, then do torch dot compile and then pass the module which was there. And here if you mention nothing, then there is if there is nothing here, there is no parameter here, the mode, then it would be doing default mode. Now default mode means like there are modes, various modes are there. Like default mode means it shall be compiling, but it shall just be compiling. At the back end, like it might be using like after compile, I shall be going to the compilation stack.
I think you hold on to that for later.
Yeah. So and like this is the default, but if you use reduce overhead, this is the mode.
Come to that those later.
Yeah, yeah,
There
okay.
are more flags.
There are more flags, okay. So which you can which we can deal with later. So this is how you can compile a module, okay. So using the similar method, like if it is not a module, you can just do something like that.
What is the rationale behind compiling the model from within the like why would it be separately from within the program?
I am not getting your question.
Why would it be called not compiled? That's I'm not getting the rationale behind it.
You need to tell that you need to compile this section, right? That is how you are telling. You cannot just compile everything. Okay, so
you are selectively compiling certain.
because I shall be coming to that portions, because you cannot just compile everything because there are constraints to it, because if you try to compile, there are some non-torch functions and all which this torch compiler cannot deal with, and it shall cause additional graph breaks and all, then that is harmful in some sense. I shall be dealing with that part. Okay, so you need to selectively compile specific sections of it. But now if you consider like what your question is, like why do you need to say it, like you compile this portion. Python is an interpreter based language, right? If you do not mention anything like you want to compile, and it shall directly do that eager as in like it shall be just sequentially executing it in an interpreter loop. Okay, so if you have seen some like just in time compiler, like what just in time stuff happens is like something at the back end, like that is not our concern. But if you want to use something like some compiler level stuffs on like this PyTorch and all, even in those cases you need to just add some kind of a decorator as in like git or something like that, and then write your code. Otherwise it does not understand like what to compile actually. Are you getting the rationale?
I'm trying to understand the difference. Like suppose you have composed a new module, like
Uh-huh.
my dot module, and if we also make changes in the CPP type of.
No, no.
Then what's the difference if I execute, like suppose this my module
Uh-huh.
is part of a file called test.py.
Mm-hmm.
If I do Python test.py,
Mm-hmm.
and you are, that's one case. And second case, you are instrumenting the code with torch.compile my module.
Mm-hmm.
So like if I do just Python test.py,
Mm-hmm.
won't that if this internally called torch.compile?
No. Like as in like if your question is something like this, suppose your this program is like let it name as eager. Okay, eager is just their terminology, and you are having your my module here. Okay, and like say m equals to my module, and you are calling it. Okay, now here the eager.py, and this is compile.py. Okay, so the similar stuffs are there, but you do like compiled version of it and pass through torch compile, and then you call m underscore compile. Okay, now what is your question?
Now, what's the difference between these two? If I just do Python eager.py,
If you do python eager.py, it shall not automatically cause this compilation phase.
Basically, basically the thing is what they're trying to do in the earlier, previously everything is written as sequential code. That they call the eager what is saying now is the eager code. What they're trying to now do is they're giving a program, they're trying to create a graph out of it. That allows you furthermore optimizations. They're trying to create graph out of the PyTorch program you are actually giving it. That's the key goal of what they're trying to do. They don't want to think more of an control flow. It's not a data flow. It's more of a control flow graph that they're.
Control flow, data flow, everything is there.
That is what they are trying to do with what you will be talking a lot about effect graph. Previously, everything was a sequential code. That's not the best thing. But it is easier for program for purpose. For example, TensorFlow was by default graph. Okay, but it was not
Easy to program.
For the, yes. So now that's why the TensorFlow kind of died off. Okay. So now what they're trying to say, like, Python is great in terms of like ability to write programmability, and ultimately that's a key factor, and that's essentially ultimately wins. Okay, but you want to also get, say, TensorFlow execution model. How do you want to get there automatically? That's why the Python in 2.2 and the PyTorch compilation comes. Is that the high level thing?
Yes.
So that's the part that I wanted Abhishek to tell before he starts getting into all of this. So a lesson for Abhishek, I think you might also have. So when you're communicating, always think, okay, what my audience already knows. You have to take, and that's your, of course, there's an estimation happens. Then you want to take them from the knowledge level of A to knowledge level of B. Okay. First, make sure that put yourself in their shoes, not what you know or what you have done. In their shoes and say, like, think that what audience might want to know first. Like, think of it, like, if you're learning something new, you want to know why the hell these guys are doing so much of complicated thing before getting into the challenges and so on. That's and at a high level. Give that view fast. Okay. Does that actually starts making sense like why they are after?
No, I think his question, high level question was, I guess, was given a module, so there is a class called my module, right? Why are they expecting the developer to write short compile again when they could have done it already? Right? So for example, you
don't want an annotation.
Yeah, he does not want that instrumentation.
What's the rationale for that?
So that community has brought it down to one line of code change and is complaining.
I think that is his question.
Yeah, so
you go ahead. There is an answer for that.
yeah.
You answer that question.
Uh-huh.
Why? So what is the think of it from your perspective? It's not so big of a compiler and all this thing. Why even require one line of code change? Can't actually give them this code, figure out what to do compile, what not to do compile, and
Yeah, so basically what my hunch is, so they use this annotation, okay, to mention ki like what module to compile. Okay, this is the first point. Okay, you get that point, right? They are saying what to compile. Now I personally tried something ki there was a main method, okay, and internally I was doing entire crap whatever was there. Okay, there was only a main method and internally it was doing the heavy lifting. So everything, suppose you are having a script, whatever is there in that script, you are main function and you are wrapping your main through like wrapping everything inside your main. Now what I tried to do was I tried to torch compile main. Okay. I tried to torch compile main.
We're not expecting you guys. Oh, they're not expecting you guys.
He doesn't want to leave the lab. Doesn't want to leave the lab.
So I tried to torch compile.
He wasn't sure whether they would see you or not.
So I tried to torch compile main. So think like that being said, the thing from their perspective, they could have also done something like this.
No, you tell us like what happened.
I
remember.
Yeah.
And
So
stuff happened. Like what happened?
So like initially in the very beginning of their pushes, like something like currently it is running at 2.4 in the nightly. So if you just torch compile the main thing, it shall work. Okay, it shall compile stuffs, but there is a problem in there. There are graph breaks. They like
which will make sense later.
It shall make sense later. Like it is capturing the computation graph, and if there are a lot of graph breaks, that hurts performance because you are switching back and forth from the compiled side to eager PyTorch and then going back and forth.
So
okay.
Doing that is not the most optimized. Right? You can do it, but it's not the most optimized thing.
Yes.
Because as we were talking about, there are reasons for which you break the graph. Understand what they are at a higher level trying to do. You want to create a graph of it. Although you have given a sequential code, that's why the touch compile comes in. And then there's some backend stuff with there. Oh, you want to use graph or not and stuff. It's the backend thing. We're not talking about that. Now, what happens is that if you don't tell it what you want to focus it on, it will and tell that you do it on the full main. So it is not the most at a high level. Just assume that it's not most the optimized use of touch compile. You at least at this point, you don't know future. They might come. Do it. I don't think this is why they will stop. That is why they will actually go at ultimately as Ashish was saying that you are compiling one line of code. There will be more fish like this who will complain about one line of code and then will ultimately be able to get out of it.
Yeah, because initially.
But this is a huge jump. The Python 2.0 compilation is a big jump already.
So in this case, you have to manually do an instrument torch or compile for everyone, or is it left to the developer?
Yeah. So like if you are trying to like you can choose the granularity. Okay, like you can have different functions in there, and internally that functions might be calling say like 5 modules. There might not be much graph breaks in there. You can wrap your function, which is wrapping these 4 module calls, with a torch compile. Or if you think like you want to be more granular, then you can just torch compile a particular module. Okay, so that granularity they have at hand. Or otherwise, like as you were saying, like yeah, they might come up with something automatic, but they can take in the entire code, parse it, and do it automatically. But that might create problem and creates problem as well.
Okay, now move on. Otherwise, this.
Yeah. So like it might stretch for 2 days. Okay.
Yeah,
Okay. So
and then those who join late, so the high level, what is actually happening, this is talking about this PyTorch 2.0, which is a torch. This is the next level for the PyTorch. There is an aspect we talk about that too, Episode-1 if you want to read it. At a high level, what is happening is that PyTorch expects programmer, it's a sequential code, right? On the other hand, if you got TensorFlow, where it is a graph. The TensorFlow kind of died off because it's a harder to program. PyTorch is easier to program because humans think sequentially and so on. However, even from a computation point of view, it is better to have a graph, order flow data flow graph that can actually allow much more optimizations, better utilizations, better performance. What their focus is to take the sequential code, create a graph out of it automatically, compile the Python code. That's what the PyTorch 2.0 is. Is that a one that
yes,
yes.
Now we start. Okay. So now, like I am jumping into this. Now the entire talk which I am trying to give is not that easily documented in their documentations as well. So I can, who wants to try, I can give you this notebook, okay, Jupyter notebook, then you can try it out. The point is, I have just chopped off different portions, like used internal functions and all, which a user is not supposed to use, to just show like what happens at each stages. And okay, so basically what happens here is something like this. This is a high level overview, and I shall be going into each of those sections in more detail. So there is the front end, okay, its name is Dynamo. It takes in the user script, as in like some Python script. You can like just annotate it with torch compile and all. But anyways, like that is a script. So they make use of something known as a legacy FX tracer. So there is a module I shall be coming, but FX graph is something which they already had in their PyTorch integration previously. They are making use of that legacy tracer to do some stuff and get a graph out of it. Like Dynamo and legacy tracer is doing some stuff to get a graph out of the script which you suggest, and the output is an FX graph. But like FX graph is just a container, okay, for different kinds of IR which this torch PT2 stack supports. Okay, so
also, like you might want to define what is FS graph.
Yes, everything is there. So for now, just assume that like FS graph is just a container to hold some kind of an IR. Okay, so output of Dynamo is some IR known as torch IR. Okay, then it goes through some stage which is known as AOT autograd. So what is this? Like AOT means ahead of time, and autograd means automatic gradient calculation or differentiation. So basically, this thing is necessary for training, but anyways, it passes through both for forward and backwards. It passes through this pass because it does some more stuffs. What it does is it takes your FX graph, which was in torch IR, and brings it more close to the CPP operations. Yes, you have a question?
Discussing only for the training, LLM training. Sorry.
No. It is for both training and inference. So what
Anyway, pass it through.
If I write a simple Python script, then it won't take.
It shall pass through. What I like, any Python script, it shall be treating it as a forward thing. Okay, and if there are gradient calculations involved, so that is when training thing shall come into the picture. But anyways, whether it is an inference or whether it is a training, it shall pass through this AOT autograd anyways, because apart from that training or like apart from that autograd thing, the name is a bit deceptive, but because it does something more than that. because as you see here, it takes in a torch IR and passes, gives out something known as 18 IR. Okay, and 18 is R tensor library. Okay, so that is where all like the low level operations are there in PyTorch. Okay, so once that is done, you get some IR. Okay, and then you pass it through some backend. Okay, now there are many backends available, and you can also write your own custom backend, but the default backend is torch inductor. Okay, now what happens is this torch inductor does some more stuffs, as in converts this 18 IR to something known as defined by run loop level IR. I shall be coming into that part. So that is known as inductor IR. Okay, so there are three IRs. Now using that inductor IR, they do certain stuffs like operator fusion and all, and then if you're if you are trying to do stuffs on a machine backed by CUDA, and you intimidate ki like intimate ki like you want to use like you want to make use of the GPU and all, so basically what it shall do is it shall spit out Triton code. Now what is Triton? Triton is something, I won't be saying similar to CUDA, but it is something using which you can write parallel GPU code in Python. Okay, so basically it takes in some Python code that is similar to CUDA, like it is CUDA-ish but not exactly something like that. Using CUDA, you can just write in more flexible codes and more optimized, but yeah, it does the work mostly. And then use it like it takes in a Python program which is kind of similar to CUDA and outputs direct PTX code. Okay, there is a Triton compiler there. Okay, if you
completely bypasses the CUDA as such.
yes, kind of. And
God knows how they do it. Anyway.
yeah, so there is, it is open source, but yeah, it is not clear.
Figure it out.
Design documentation is not available as such.
Ask ChatGPT for
I tried.
it failed. Give up.
At that level.
Not wanted.
So yeah, and if you are like not
Working in Microsoft research with Python, this OpenAI guys, you guys have a relation with them now.
We don't have that.
You don't talk to OpenAI guys?
We don't.
so if your backend is not CUDA, then you can just use C++, OpenMP and all, or like AVX instructions. That is how they would be trying to do stuffs on the CPU. In this talk, I won't be going to the CPU stuff. I shall be mostly considering this inductor thing and Triton part. Now let's move on from there. So let's like the basic building block of this entire framework is torch fx, some library known as torch fx, and its governing thing is that fx graph which we were talking about. It is the container for all the IRs which are available. So this fx, like I shall be first discussing what this torch fx library provides as
Like one of the confusion that I keep on having is that
Mhm.
in the mental model, whenever you are talking about these graphs,
Mhm.
in my mind there are two types of graphs in a program.
Mhm.
Forward flow graph, data flow graph.
Mhm.
This looks like a hodgepodge of both, right?
Yes, because what they do is like just to digressing a bit, it is there, but first of all they take the program, and whenever they like there is a control flow involved, they break the graph.
Yes.
Okay, they break the fx graph. So for each of the reachable portions of an control flow stuff, you have different fx graphs. Okay, then using control flow analysis that the Dynamo does, they instrument the original bytecode during runtime. Okay, and they somehow stitch the this after you have got this fx graphs, you compile it and you get a compiled module. Once you get the compiled module, you get a pointer to it and all, and they somehow stitch this compiled code together using the bytecode level using bytecode rewrite. Okay, that is where this control flow thing comes into the picture. Now for each of this fx graph, so there is something known as like they call symbolic execution, that is not static execution, not dynamic execution. So they take in some symbolic tensors, as in like they name it as fake tensors, pass it through it like some kind of a taint analysis they do, and they get
Essentially kind of a data flow.
yeah, that is where the data flow thing
But
comes.
that can go wrong during the actual execution, no?
No,
With
it
symbolic
no,
execution
it
should not be able
it no
to-
no no
should
no
not be
no
able
no
to
it
take everything, no?
it won't do that, because
Or you
they
will give up while they will put
no they have something known as guards.
Ah.
They track it, the data type. The moment something changes, like everything, every time there is a guard
Go
check.
back.
Whenever there is a fail, it shall, that is what I was saying. It shall trigger and it shall stash everything and do recompile again. Just like that.
So for the so basically what is going on? At a very high level, in computer science you typically know two graphs, quantum flow and random graph. This guy is huge, much further. So basically they are still starting with the basic blocks, because as soon as there is and that is the that is what they are like related to break. This is in a quantum flow they are actually breaking, right? But then they are doing symbolic execution. I guess you guys know symbolic execution, Deepak teaches and so on, right? To figure out how this will actually supposed to get executed. But they have also, should we call it callback or some
Continuation or something.
Yeah, where if they figure out that at runtime things are not going as they expected, then they actually go back and redo the whole thing, recompile, essentially recompile.
Yes, recompile, and they maintain cache. There's like
Extreme level of complication.
yes, but things are performing good. Yeah.
Managed rate.
Yeah, like they are getting around 2.3, 2 point something to 3x improvement just by doing this.
Because they have gone to the graph, huh? Graph execution.
Yeah.
I have a- So,
Uh-huh.
what the symbolic? So, what to go wrong? So why do they need to recover?
Independence.
Yeah, suppose just giving an example, you traced your program through some float thing, okay, or to be very easier, like you passed a tensor which is there on the GPU, okay, the device option is having CUDA, okay, you passed through it. Based on that, this program expects ki like you shall be getting a GPU tensor, okay. Now suppose while execution suddenly you pass a tensor which is on the CPU and you just allow it to run. What shall happen? You shall be dereferencing a CPU pointer on the GPU side, and it shall lead to illegal memory access on the device side. So that shall be a problem altogether. So like how did you know ki like it is during symbolic execution, you just do symbolic analysis of something and get ki like this tensor is expected to be there on the device, and based on that you have some guards, okay, as in now suppose suddenly during runtime you get a tensor which is on the CPU, so one of those guards shall fail, the check is there like this tensor shall be on the GPU, so this fails. So as a result what shall happen is it shall say okay, I do not know this pattern, so keep aside what I have compiled till now, let me recompile it and like kind of a dictionary, okay, so for this kind of thing I shall be executing this code, this thing I shall be executing this code. Am I able to make sense?
Are those cards aggregated by ATEC underscore switch?
No.
Because I've been going to the CVP code, like CVP to see if it's on CPU or very fast.
Like I haven't looked into the C++ side of it, but
It will be most like they use the same framework.
I don't, like I need to check. I have not seen the C++ side of thing. This guard thing is very complicated. But anyways,
These guards are added automatically in the compilation.
yes, like these guards like entirely they are it is maintained by them.
I think so in the detail are annotating this to check because there's something called ATEC underscore switch.
Okay.
They pass the tensors and see this on the C for the GPU, then they do the operation.
But
They are probably pushing that while creating the IR.
But what I saw, I had a rough while making this documentation. I saw some rough code. but there is like dynamo, like in the virtual environment which you create, right? So like as in here there is torch slash fx, there shall be something known as torch underscore dynamo. There shall be a guards.py file. Okay, that is dealing with the guards in the dynamo.
and couple of the CTP levels.
Yeah, so
Maybe that
like
is not
that guards.py might be wrapping something in the CPP level, but I don't know as of now. It's very complicated. Anyways, might be. I shall have a look. Anyways, yeah. So I shall
So
be.
one question:
Huh.
if there is an application
Mm-hmm.
which is based on this input, why multiple times you are requiring recompilation,
Mm-hmm.
could then not actually lead to performance loss?
Yes. So like they have a limit. They have some magic logic inside it. If they say, if they see like certain input pattern is causing recompilation, they stash everything and
Then go to eager mode?
switch to eager mode automatically. They have this logic built into it. The limit is something like 2000 or something like that. After that
Because
basically,
it's a cost, right?
yes,
You're at
it's
a
too
runtime
much.
you are paying this cost.
Every time if it is there, it shall check after certain. Uh-huh.
The flag show like if your program is getting recompiled.
Yes, there is a flag. And there is also a flag, ki like if there are too many recompilation, push it up as an error.
Right.
Just instead, like before doing it to before doing switching to automatically eager mode, because you don't understand whether it is
So
compiled.
you are actually telling the programmer like,
Yeah.
hey, this is happening. So if you want
It is
to
an
do
error.
something about it.
So there are many kinds of flag. Like if there is a graph there, you can also raise it as an error.
This is callback you can
Yes.
essentially you can- yeah.
Yes, there are many stuffs. It's very nice. So first of all, I shall be dealing with this fx graph thing. Then I shall slowly build up ki like how Dynamo uses this to get the stuffs done. So this fx library consists of three things mainly. So symbolic tracer, which shall symbolically trace your Python code and create a graph out of it, which is actually the fx graph, and which shall be having a graph module backend backing. I shall be coming into that part. So intermediate representation is that fx graph, and like there is a Python code generation of it. Like whenever you are capturing a graph, so corresponding to it there is a method using which you can get a Python code automatically out of it. Okay, now if you like, that is some methodology which they have provided. So like if you make some changes to the graph and you can just do dot like generate code or something like that, it shall spit out the Python code corresponding to your modified graph. Okay, so shall be coming to it. So basically if you see here, there is a program. Okay, so params is like the parameter module, like passing through it, and like it is taking some random tensors of size 3, 4, like, and there is some, this is another linear module. So this is the forward method, okay, of this module. So if you see here, it is too much nested, but anyways, like you are passing in x, you are summing it with linear dot weight, and then you are calling linear on top of it, and then passing it through relu, and then doing dot sum out of it, and then you are getting the top 3 of this. Okay, so this line is important. Now what you can do is to make use of fx graph, you import something known as symbolic trace. So symbolic trace shall gives output, like this is type annotation, it shall give something of the type torch fx graph module. I shall be coming into this, but basically then what you do is, you here what I did was I instantiated this module in like my module into this module variable, and I pass this module through symbolic trace. Okay, it shall be giving some output. So what is that? I like did the type of this symbolic trace and try to print out what is there in symbolic trace. If you see, the type of symbolic trace is fx torch.fx graph module. Like let's not go into the details of other stuff, but it is a graph module. Okay, and the output is something similar to what, like it does not show much, like it just shows like it is my module. Okay, even if you symbolically traced it, it is like my module was the original one, symbolically traced prints out the same thing. It is a my module. So if you take the symbolical, like symbolically traced has an attribute. Okay, so symbolically traced, the output is a graph module. Okay, so now what is a graph module? Let me go into that. So basically, if you are provided a PyTorch program, okay. So suppose this is a .py file and you have some code here. I am not talking about like torch compile or something like that now. I am just talking about the legacy tracer of fx graph. So if you have this symbolic tracer, okay, it shall generate some graph. I don't know why it is lagging. Hardly it is readable. It shall give out some graph which is fx graph. So this fx graph thing is like, suppose you are having this my module which we saw, right? Corresponding to this is this, there shall be something known as like some module which is a graph module. Okay, hard, I don't know why it is lagging, hardly any writing is visible. So this graph module is what shall be wrapping against this fx graph. Okay, now how it happens, why it happens, so I shall be coming into each of those sections slowly. Okay. So if you see here, you remember that original program, this, see this line is important here, I just showed it. Now if you try like this graph, like this dot graph is like the graph module has an attribute which is the fx graph, which is holding a pointer to your fx graph. Now if you try to print that graph, you shall get an high level IR kind of thing which shows you the graph in a textual format. So placeholder is actually your input x. So if you just compare it, so this is your input x, it got replaced to something known as placeholder. Okay, number of users is like who is using that, but anyways, uh, get attribute is like the target, like it is mentioning the target is x. Similarly linear dot weight, like get attribute is what is doing, self dot linear dot weight, the dot is an attribute. Okay, so that is the reason why it got converted to something known as get attribute. Then there is a call function. This call function is called to some generic function. Now what is a generic function? So like in Python, each of this like plus and all, they are operators, but they are having a function backend to it, so they are operator overloaded. So this call to some this addition changes to some plus thing. Okay, like some function call. And similarly, if there is a method call means something which is inheriting from that nn module and having like nn module, and it is an nn module after all, and you are calling that function as a like this is that you are having that dot linear here. So basically if you walk through it and like this line of code, right, it just dealt with the forward and it got changed in some IR format. Okay, we shall go into it more in more detail soon, but if you do symbolically traced dot code, this is what I was talking about. Every fx graph has a code backing which is generated automatically, like some Python code. If you see here, the same thing, it is represented in a more decomposed format, right? That single line, this is generated automatically out of the graph. See that? Okay, like linear weight, like self dot linear dot weight, then add is adding this self dot linear add, everything which was there, it got replaced by a single line because it is just generating this code automatically from that graph which it captured. Now one point is, why is this wrapper graph module which I told you, right, important? The point is, Here if you see, we are trying to do something as self.linear.weight. This self thing is something specific to this particular module, if you can understand. So if you are having some parameter that shall be there in this particular module and this particular module's instantiation. Now what this symbolic trace outputs, it is an fx graph module. So why do you need this graph module altogether? It is because the way they write this code, right? If you see this forward method like symbolic trace dot code, you see like there are references to like self dot linear dot weight. What is this self dot linear? Okay, in this new graph module, like you cannot just access some other modules attributes in that manner, right? So what actually happens is when they are symbolically tracing it, they create a graph module which internally has the IR and all, and while tracing, what they do is they also capture the original module's parameters and attributes, if any, so that they can use like this in this new module's forward method, which is getting generated using self dot that name. They can get hold of something similar. You got the motivation regarding this graph module?
Is this something you and Python should or?
Yes, this graph module is something totally.
And this symbolic trace must
Yes,
be
symbolic trace was like this. Sorry, this symbolic trace, this graph module, something. It is not something. It was there before, like PyTorch 2.0. This is something which they're reusing. This is something known as legacy FX tracer. It was there previously. They might have enhanced it with the like to go hand in hand with this PyTorch 2.0 stack altogether. But this thing was there even before PyTorch 2.0 came into.
symbolic tracing was there. They just have this graph module.
No. Everything was there. Like whatever I am talking right now is not related to PyTorch 2.0 anything. Like this is just a library which they are using rigorously. Okay, this has nothing to do with fx graph like dynamo or torch compile altogether. So like yeah, I just explained this. Like there is a code generation stage, like there is this fx graph kind of acts like a source to source, like Python to Python code transformation mechanism. So how can you use it? Okay, but before that, quick primer on the graphs. So if you take a kind of similar model, but I reduce the complexity of this line. If you see here, if you symbolically trace it, like this graph module has a graph attribute, you get the graph, and this graph is fx graph. Okay, fx graph is a different class altogether. It is a data structure. Okay, now if you try to print it in a tabular method, so SLC, each like the left hand side, each represents a node in the fx graph. Each node has an opcode related to it. Okay, as in you can compare it with some kind of instruction set architecture. Okay, so each instruction is represented by a node, and each node has an opcode, and as in just as you have an instruction, right, there are like what it tries to do, like target, like as in target means you need to call something. Okay, something like that, and then name is the as in the variable which stores the operation of that. So and then there is this keyword arguments and some metadata stuffs. Like this field is important when they do symbolic trace and all to get hold of data type and all. So I shall be coming into that part shortly. So then if you take this, we saw this part. Okay, like, this graph module, if you do print readable, it shall be printing that code corresponding to that graph, like in some format. Okay. Now,
This is different from the symbolic trace.
yeah, this is symbolic trace, right? Like I did symbolic trace here.
The, this whole spot on Yeah, this print readable that you showed, right?
Mm-hmm.
Is it different from the hover that you showed?
No, no, no. This is the same context, right? This is graph module. Like this scope is still there. This graph module.
Scroll up. Yeah, this print symbolic trace part.
Yeah. This is the same thing, but they are accessing it like I accessed it at like a code level. Print readable is the same thing. Okay, this is the code. I just wanted to show कि like there is a code corresponding to each symbolically traced graph module which gets generated corresponding to that fx graph. Now you see here कि like to maintain any information what you need is just like inputs and outputs. So basically this placeholder is your input, this get attribute a certain other outputs, and output is the return statement. Okay, so that makes it clear in some sense. That is what I wrote here. Now let's do some graph manipulation and see what happens. Okay, so it is interesting here. Let's take a sample module, and in this forward what I am doing is like I am taking two tensors and just adding them up. Okay, now let's have a transform module. What it does is it takes in say my module. Okay, and this is a like just to mention here, this tracer class is something which is there inside symbolic trace. The symbolic trace which they are doing it here, right? Okay, this method internally has some tracer running inside it, so I just brought it out here. Raw tracer class, I am tracing this module here.
M is an object of class M or module?
Which one?
Sir,
Module.
Like
the
this
base
is
class
this is
right?
inheritance, right? It shall be
Okay.
So which M are you talking?
Like in
This-
the
this-
transform function, the argument is type
Like-
module.
Huh.
But then why don't you define the class M?
what? Oh no. This torch.nn.module is the base class.
Of capital M.
Yeah, capital M. Like this is the base class of all modules. It has nothing inside it as of now. Like I created a specialization out of it. But like if I just say type, if I do just type of M, right? This capital M, it shall show okay, like torch.nn.module. That is how it works. Okay. Now even if I say M and pass it capital M, like even if its type is torch.nn.module, and if I pass in capital M, it shall work because that inheritance structure, right? You can just classify with the parent class as well, and it shall just work. Okay.
The first variable is always the object
Yeah.
and what function.
Yeah.
We make it.
So the tracer class is like default is torch.fx.tracer, and you trace this module which is there. So output of this tracer class is fxir, fx graph. Okay, not graph module. Graph module is an output of this symbolic trace. So I am just dealing with fx graph right now. We get a graph. For each node in graph.nodes, what I do is I iterate through it. If it is a call function call, what I do is I change the node's target from add to multiplication. Okay. I change the node's target, that particular node's target, what function pointer it is having. If it is torch.add, I assign it to torch.multiply. Okay, and then this is how it is happening internally in this phase is not actually this transfer, like iteration through nodes is not there in symbolic trace. Okay, they just create the fx graph and just pass it through this torch.effect.graph module constructor. So this shall give you a graph module as output. So what do I get as a graph? This is new symbolic trace with a transfer function built into it. So now what I do is just to show. So this is 1 2 3 4 5, and I just instantiate a list of 2's. So if you just instantiate M as if its own and just pass xy, this xy, it shall be like 2 plus 1 3, 2 plus 2 4, like adds increments everything by 2. Okay, now what I do is pass like this method which I created, right, transform, pass m through it and get a transform module, symbolically tracing it, changing the graph and getting a new graph module. Now if I pass xy, it doubles it. That is how you can do, like, make changes through effects. Like,
What is significance of trying to relate something?
no, like this is how you can make changes in your graph. It shall make sense when I go deeper into the dynamo stuff. So this is just an example of how you can make changes to your IR. You can make changes to your FX graph or IR and spit out a PyTorch code which is having a totally different output, like behavior altogether. So basically what you can do is like fuse one or two operations together and have a different functionality altogether. My point, what I want to show here is, once you have the FX graph out of it, you have like a lot of power to deal with code level changes and all.
I think the high-level point that I was trying to think of it as an LLVM pass or a compiler pass that you can use to transform your code to still ensure functional equivalency, but be better.
Try to combine the road power or rewrite your code. Simplify cubes and yeah, you can do everything in the like
Yeah, you can do it at the
idea is more structured.
Yeah, to
you
make
have to deal with only few instances. Python can be so much like when you lower it to IR, you basically lower your code to a smaller subset. You can always reason about that.
yes, like basically
They do automatic fusion.
yes, that is my motivation is they can do that very easily once they are having that IR. And we also tried getting some IR out of a Python code as is a pain, and there is no such tool available as of now which does it very soundly. Like there are few available, but they are mostly crap, does not serve the purpose, but they are able to do this. Okay, so I guess we are out of time now. I shall be continuing it in the next meeting.
Yeah, I think we should continue next time we meet actually.
Yeah, Wednesday.
Yeah.
Yeah, because unless I deal with those stuffs, it won't be that torch dynamo won't make sense because people won't understand it. Okay.
Oh, fine, thanks.
Okay. Neha.
Yeah, close the meeting.